So today, we're going to dig into a truly elegant data structure. Think of it like an architectural blueprint, one designed to tackle one of the biggest bottlenecks out there in computing, just getting data from where it's stored to where we actually need it, and doing it fast.
Yeah, this is really a story about how a super clever design can outsmart the raw, brute force limitations of physics.
Okay, so this slide right here, it gets right to the core of the whole problem. Your computer's processor and its storage, it's like they're living in completely different time zones. Getting data from the CPU cache is like reaching over and grabbing a book that's sitting on your desk. Easy. But asking for data from an SSD? That's more like getting up and walking across a library to find the right bookshelf. And a classic spinning hard drive? That's like getting in your car and driving to a library in a whole other city. This huge gap in speed is the fundamental challenge we have to solve. All right, let's get into it. To really get why the solution is so cool, we've got to first appreciate the actual physical problem we're up against with our storage devices. With those old-school spinning hard drives, the bottleneck is, well, purely mechanical. There's a tiny little head that has to physically fly across a spinning platter just to find the right spot. It's kind of like waiting for an elevator in a huge skyscraper. The time you spend traveling is most of the weight. And even with modern SSDs, which don't have moving parts, there's still physical limits that make certain operations way more expensive than others. So how in the world do you work around these laws of physics? Well, you don't fight them, you get smart. You build everything around one single foundational blueprint, this concept of pages. And really, the entire strategy hinges on this one super powerful idea, spatial locality. The logic is actually pretty simple. If you're going to make that long, expensive trip to the library in the next city, you don't just go for one book. No way. You grab a whole stack of books you think you might need soon. You make that trip count, right? And here's the kicker. The hardware itself is already built this way. Your storage is organized into these things called pages or blocks. You literally can't ask for just one little byte of data. The hardware makes you request an entire page at a time. So the goal for any smart data structure is to make damn sure that the data we pack into every single one of those pages is as useful and relevant as it can possibly be. All right, so with that foundation in place, let's see how we can use it to build one of the most important data structures in all of computer science, the classic B-tree. Building a B-tree is actually, super logical when you break it down. First, you take advantage of that spatial locality thing by grouping a bunch of related keys together on one page. Step 2, you keep all those keys sorted inside the page, so once you've paid that heavy price to load it, finding what you need is lightning fast. And finally, you just use pointers to link all these pages together, and bam, you've got yourself a tree. So here's the really clever part about the design. B-trees are built to be wide and shallow on purpose. See, every single level you have to go down in the tree could mean another one of those slow, painful trips to the disk. The whole goal is to make the tree as short as possible, which means you're minimizing those drives to the library. Okay, so the B-tree is just a brilliant piece of engineering. But, and there's always a but, right? This classic blueprint has a hidden flaw. There's a detail that makes it kind of fragile, totally dependent on the specific environment it's built for. And this quote right here from one of the original papers, it basically points a giant finger at the B-tree's Achilles heel, the device-dependent natural number k. This k is just the magic number that says exactly how many keys you can cram into a single page of the tree. And that is the huge problem. Device-dependent means that to get the best performance, an engineer has to know the exact block size of the disk, the cache line size of the CPU, all of it, and then manually tweak the B-tree settings to match. It's like the blueprint for the data structure has the hardware specs written right into it in permanent ink. So that brings up a really critical question, right? It's like you're an architect with a blueprint that only works with one specific size of brick. What happens when you need to build somewhere else with different materials? What do you do if you don't even know what size the bricks are going to be? So, how do you fix that? Well, you do it with a self-adapting structure that solves the problem with just breathtaking elegance. The Cache-Oblivious B-tree. I mean, the name really says it all, doesn't it? It's oblivious to the cache. This is a design that somehow gets the best possible performance without needing to know any of those nitty-gritty hardware details like block size. It just works. So how on earth does it do that? Okay, the secret sauce here is this incredibly clever way of storing things called the von Emde Boas Layout. Instead of just using pointers all over the place, it lays out the entire tree in memory in this very specific recursive pattern. Basically, it makes sure that whole subtrees are stored together in nice, continuous chunks. And that's what's so amazing about this recursive layout. Because it's kind of fractal-like, it automatically maximizes that spatial locality thing at every single level. So when a disk reads a big block of data, it just happens to grab a big, useful piece of the tree. When the CPU cache pulls in a much smaller line of data, it grabs a smaller but still totally coherent piece of a subtree. It works automatically no matter what the block size is. The structure adapts to the hardware, not the other way around. So when you step back, you see we've gone from this rigid, hard-coded blueprint to one that's flexible and totally adaptive. And that really gets you thinking, doesn't it? If we can design data structures that automatically adapt to the physics of hardware, what's the next big step? Could we build systems that adapt to us, that learn and conform to the patterns of the people who